Okay, let's do another question from simple harmonic motion. The uniform stick of mass m, length L, is pivoted at the center in the equilibrium position shown in the figure. The identical light springs have their natural length. If the stick is turned throughout a small angle theta, it executes simple harmonic motion. The frequency of the motion is, so that is I have fixed horizontal walls like this. I have two identical springs, spring constant K, and these springs have mass, light springs, and there was uniform stick of mass m and length L. It pivots at the center. So then this length is L divided by 2 and this also L divided by 2. So that it is free to rotate in this plane. This is the uniform rod. So where will the center of mass? It would be the center, is this pivoted point. Now the question asks this: if I displace by little angle theta, what would be the frequency of the SHA? Frequency of simple harmonic motion that it does. As we know, A equals minus omega squared x. As like this in the rotation, alpha equals minus omega squared theta. Okay, we will be trying to find this relation. This is linear acceleration and this is angular acceleration. Equals minus omega squared is the constant value. This is linear displacement and this is angular displacement. Linear acceleration, angular acceleration. Linear displacement, angular displacement. So I am actually drawing the diagram with the large theta. But this theta consider to be small because it's given in the question. So this was my natural length. This is theta. So this would be L by 2. This also would be L by 2. So let's talk about this point. I'll get C. This is uniform stick length L. And its mass act on this point. Because center of mass in this rod is at C. So you can see that rod, whether it is on horizontal or vertical, that weight of the rod mg passing throughout the C. So there will be no torque from mg. This rod pivot at point C. So how much there's force from the spring? This force is actually equals to this spring constant into elongation. So what is the elongation? This elongation extension is equals to L divided by 2 into theta. Not actually theta. It would be L divided by 2 into sine theta. This is L divided by 2. This is theta. This is L divided by 2 cos theta. And this is the extension. It is L divided by 2 sine theta. This also L divided by 2 sine theta. Then I can say the force act on the spring, single spring, F equals K multiplied by L divided by 2 into sine theta. We can see right triangle in small theta. But actually you can see when theta is small, sine theta is approximately equals to theta. Approximately equals to theta. In this case, this extension L divided by 2 sine theta is approximately equals to L divided by 2 into theta. So what would be the force of the string? I get F equals K multiplied by L divided by 2 into theta. So this is the force on the string. So what would be the torque of the spring throughout C? Torque from single spring, force multiplied by perpendicular length. Now I can say torque equals force is there, K L divided by 2 into theta multiplied by perpendicular length L divided by 2. This is the torque is provided by the single spring throughout C point counterclockwise. The same torque would be from this spring. It's also counterclockwise. Because the extension is same and perpendicular length also same. So I just have twice this is the total torque. K L divided by 2 theta L divided by 2 multiplied by 2. Cancel this 2 to 2 equals K L squared theta divided by 2. As you know, this is the torque and also this is the couple of moment throughout the point C is the pivoted point. Okay, now we can apply tau equals I alpha. This I is the moment of inertia. The total torque as we are find out is K L squared theta divided by 2. So now what would be the moment of inertia of this rod? We know it. At the moment of inertia of the rod, about its center is ml squared divided by 12. Moment of inertia multiplied by alpha. So then cancel this L squared and cancel 2 is there 6. Then I can subject as alpha, angular acceleration alpha equals 6k divided by m theta. Now we have alpha equals 6k upon m into theta. As you can see, this is the displacement and this is the force. As like angular concept, the torque would be counterclockwise, but the angular displacement is measured by clockwise. We know in simple harmonic motion, all displacement and angular displacement is measured from its center of oscillation. Think about this angular displacement and torque. Both are at opposite direction. Angular displacement, torque, both are the vectors. In the equations we are using, there was lot of vectors. But consider the one thing. All the vectors in your equation must need to act same direction. It may be left or right. It may be counterclockwise or clockwise. In this case, this angular displacement is measured by clockwise, but the torque would be counterclockwise. Yes, we know in simple harmonic motion, the force will produce opposite the displacement. Torque will produce opposite the angular displacement. So I'm gonna change the direction of theta. I apply small sign minus there. This minus sign on this theta. So the angular acceleration is counterclockwise and theta also counterclockwise. Now all opposite vectors respectively in same direction. We know the standard equation of simple harmonic motion A equals minus omega squared. In the rotational case, we can apply same as alpha equals minus omega squared theta. Now I'm gonna compare with this equation with alpha equals minus omega squared theta. Okay, here we go. Alpha equals alpha, minus sign, there's minus sign, equal sign, here they are equal sign. This theta, as here this theta. Okay, we can find omega squared equals 6k divided by m. So then omega equals root 6k divided by m. We need to find frequency now. We know omega equals 2 pi f. I'll just write that 2 pi f equals under root 6k divided by m. Now the answer is frequency equals 1 over 2 pi under root 6k divided by m.